Okay, let's get started. So, 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 right. Uh, okay, for the midterm exam, so we will take the midterm exam on April 24 during the regular class time. Okay, and then we will take the exam in this place. Okay, so we will take the exam on April 24. And then for the April 22, the no class. So we will not have a class on April 22. Okay. So because I need to participate in the project evaluation, so I cannot I cannot teach. But unfortunately, so this is the exam week. So I think it's good. It's good for you, right? And then so I will record the lecture video, and then I will post the lecture video later. Okay. So no class on there. We will not have class on April 22. And the midterm exam will cover so what we learned so until the where is the so we have 3 classes including today's class until the midterm exam. Where is the calendar? Okay, so so exam will cover the what we learned until the April 17th. Okay. Okay, and then so as announced, the exam is the closed book exam, and then you cannot use any electric devices except the simple calculator. Okay, so 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 we learned about so actually you may calculate the execution time. Also, you may compare the performance, right? And then it means you require a simple calculator, right? And then, but you cannot use any other electric devices, so such as smartphones. It's not allowed, right? And then, so okay. Any questions about the exam? Okay, good. So So we are learning about the arithmetic hardware on CPU, right? And then, so in chapter 2, we learned about the RISC-V instructions. And then, the RISC-V instructions include arithmetic operations, right? Like add, subtract, multiply, or division, divide. So it means, so our hardware, our CPU needs to include the processing units for supporting these operations, right? So actually, if you took the digital logic design course, and then I believe you learned about the ALU. So it means the arithmetic logic units. Okay. Actually, the CPU includes ALU, and this ALU is used for computing arithmetic and logic operations. Okay. So it means the most instructions are handled by ALU, right? So that's why we are learning about some arithmetic for computers, okay? So, and then in chapter 4, we will learn about the hardware architecture, right? So that's why we are learning about the hardware implementation of the arithmetic operations. So we learned about the addition and subtraction because, so, the binary addition and binary subtractions are very simple, right? So like the decimal numbers, we can just apply this binary addition and binary subtraction. Subtractions are also just the addition, right? So we can just use the negative number for subtraction. So if you see the RISC-V instructions, you can find that the RISC-V includes the add instruction and sub instruction, right? For the R-type instructions. But RISC-V just has add I. So for the immediate instruction, the RISC-V has only add instruction. Why? Because we can use the add I minus number, right? So, the immediate number is the signed number, right? So actually, so if we use the negative number for the immediate field, then it's subtraction. So that's why the RISC-V has only add I, not sub I. So we there's no sub I instruction in RISC-V. Okay. But anyway, it has sub instruction. Okay. So multiplication. So multiplication is a little bit more complex than the addition. So why? So so in arithmetic, in normal arithmetic, so we know that the multiplication is more difficult than the addition. So think of think about your elementary mathematics, right? So, but it's simple, right? So like the decimal numbers, then we can just apply the same approach for the binary multiplications, right? So in this is the example. So the multiplication also includes the two input operands, right? So multiplicand and then multiplier. So A multiply B. When we compute A multiplied by B, and this is the multiplicand, and then this is multiplier. Okay. Then how can we perform? How can we perform multiplication? It's a simple. For each digit of multiplier, we can generate the product. Okay, we can just perform multiplicand multiplied by each digit of multiplier, right? So then we can generate the product, okay? And then these numbers are called the partial product, okay? Partial product. So for each digit of a multiplier, we can generate the partial products like 1, 0, 0. But this is the binary number. So each digit of a multiplier has only 1 and 0. So if this number is 1, then it's same to the multiplicand. The partial product will be the same to the multiplicand. And then if this number is 0, then the partial product is 0, right? It's simple. And then we can just accumulate all partial product to generate the final result. So it's called a product, right? So this is the multiplication. But multiplication is more complex than addition. Why? Because for addition, we can just perform the addition of two numbers, right? But for multiplications, the multiple partial products are generated, and then we need to perform additions for these partial products. So that's why the multiplication is more complex than addition. And then also the size. The size of multiplier engine is larger than the size of addition adder, right? But this is the implementation of multiplication. So actually, we can implement the multiplication like this. So actually, so in this example, so we can just consider the position of this digit of multiplier, right? So based on the position, then we can just perform the shift operation, right here. So for this digit, there is no shift, and then then for this digit, then we need to perform the shift by left, shift left by the one digit. And then this is shift left by two digit and three. Okay, so then we can accumulate this generated partial product. So this figure shows this operation, shows the shift operation by the digit of each digit of multiplier, and then it's accumulated. Okay, so this is the some diagram of a multiplier. Okay, and then as I mentioned, we can implement the multiplier using the shift operations, but it's too slow, right? So for example, actually, for this using this hardware, so we need to calculate the firstly, we need to generate the first partial product, and then we generate the second partial product, and then we perform shift operation, and then these partial products are accumulated, and then the third partial product is generated, and then it's shifted and accumulated. So what's the matter? We are designing hardware, right? The hardware, and then so the hardware hardware engines have delay. Okay, so so we need to implement this hardware using CMOS logic, right? The CMOS transistors. And then, actually, so if you took the digital logic design course, then, these hardware engines are composed of basic logic gates, right? And then, the basic logic gates are also implemented using CMOS transistors. And then transistors have delay, right? So it takes time. Also, in order to control this operation, so we need to use the synchronized logic. So it means that it's synchronized by clock signals. Okay, we need to use a sequential logic. So clock cycles can be wasted. It can be taken. So not wasted. It's used for computation, but it's taken. That's the problem. Performance, right? Because we need to reduce the number of clock cycles for executing instructions, right? But if we implement the multiplier hardware like this, so firstly, generate the partial product, and then perform the shift operation, and then accumulate it. Then, so for example, if this number is the 32 number, and then we need to repeat this operation 32 times, right? And then it may take 32 cycles. And that's very long. So it's a very high latency. So it's not good. So if we just consider the performance, then it's not a good design. Then how can we improve the performance? Okay, so this is the some algorithm for computing binary multiplication. So, right? Then how can we increase the performance? Parallel operation, right? So actually, even though when I explained that so for multiplication, the partial product is generated and shifted, the partial product is generated and shifted sequentially. I just explained that these operations can be performed sequentially, but actually these operations, and then these operations can be done in parallel, right? So right? So you can just generate these partial products in parallel, and then we can just accumulate the all partial products. Okay, so actually, uh, multiplier, we can just implement the fast multiplier using this approach. Okay, so so now, now we are going to the hardware. So actually, until the chapter 2, is the software world, right? So we just learned about the instruction or assembly instructions, and then we are going to the hardware world. So which means we need to consider the hardware implementation, and then when we implement hardware, then we need to consider the performance, right? So it's a parallel operation is possible. So when we can implement the multiplier like this, okay? So the partial products are concurrently generated, and then these generated partial products are just accumulated using adder tree. You can find the many adders here. So these are partial products, and then many partial products are accumulated by the adders. Okay, and then so the results are also accumulated. So using the adder tree, that we can implement the fast multiplier. It is because parallel operation, parallel computation is available for multiplication. Okay. And then, but compared to also compared to the adder, then but you can find that there are many adders here. So it means it will take longer time, right? Compared to the adder, then it will take longer time. So it can be pipelined. So we will learn about the pipeline later. But so if the actually so this is the combination logic, and then this is the deep flip-flop. So digital logic, digital system can be implemented like this, right? So there are flip-flops, and then between these flip-flops, you can find the combination logic, and then combination logic is required for generating some result, okay? But combination logic, except the delta t, it's a delay, and then clock period. The clock period is determined by this delta t. And why clock period is critical? It's because, t execution, instruction count, CPI, multiplied by TC, clock period, right? So if this delay is too long, right? So if delta t is very high, then we can just split this combination logic part into multiple parts. Then we can insert the D flip-flop to reduce the delay, the critical delay. So this is the pipelining actually, right? This is the concept of pipelining. So because the multiplier hardware is more complex than adder, so we can just insert the D flip-flops between these steps, right? Then we can reduce the critical delay, okay? So this is the pipelining. So RISC-V also supports the multiply instructions, multiply instructions, right? But in order to use these multiply instructions, so we need to add the multiplier or divider extension for RISC-V, right? We learned that the integer RISC-V is the baseline of RISC-V instruction set. And then in order to use other instructions, then we need to add some extensions, right? And then for multiplication, so in order to use the multiplication, then we need to add the multiply or divide extension, okay? So I believe you are doing a lab assignment, right? So and then when you build the RISC-V cross compiler, and you can find that we define the target architecture, right? And the target instruction set, right? So you can find some options like m arc. So I don't remember the exact name, but after these options, we just define the IV32I, okay, like this. So it means it generates the compiler which only includes IV32I instruction set, right? So it means if we use the multiplication in our C code, then the multiplication is translated into the some other instructions, right? But if we use the uh, multiplication option, extension like M, then we can use the multiply instruction, right? So mul is the multiply, and then it gives the lower 60 bit of the product. So what does that mean? If we just perform 32-bit by 32-bit multiplication, then the product will have 64-bit, right? It's the same for the decimal multiplication. So 2-digit multiply 2-digit will generate the 4-digit numbers, right? So actually, if we just perform multiplication, then the bit numbers can be increased. So more just to give the lower 60, not 60 bit, it's a 32 bit. Okay. So I did not. It's a 32 bit, it's a 32 bit, it's a 32 bit. Okay. And then so it just gives the lower 32 bit of product. And then if we use the mul H, then it just gives the upper 32 bit of the result, the product. And then we can also use the unsigned or signed, unsigned options. Okay. So 32 bit. Okay. So this is the multiplication in RISC-V, and then division. So how about the division? The division is the inverse process of multiplication, right? It's just the inverse process, but division is more complex than multiplication. Why? So this is the example. So when we just perform A divided by B, then it generates the quotient and also it generates the remainder. Okay. So this number A is the dividend, right? And then B is the divisor. And then we just perform a division operation between A and B. Then result is the quotient, right? But this is the integer division. So if we just perform division like this, like 5 divided by 2, then what's the quotient? Quotient is 2, right? So it just generate the integer number. So in order to generate the floating point number, then we need to use the floating point numbers for dividend and divisor. And what is the remainder? Remainder is 1, right? So this is the division of integer number, right? But why division is the more complex? So this is the example. So let's see how we divide the numbers, right? So this is the dividend, and then we check the digit of dividend with the divisor, right? And then we just compare the first 4 digits because the divisor has the 4-digit numbers, right? So, and then we just compare the magnitude of dividend and divisor, right? And then if the dividend is larger than divisor, then the quotient 1 is generated. Then what's the next step? We just subtract the 1000 is a divisor from dividend, and then this number is generated. Actually, we just compare 0010 with the 1000, but 0010 is smaller than the divisor, so quotient 0 is generated. And then because this dividend is smaller than the divisor, we do not perform subtraction. We do not subtract. So what can you observe? For division operation, we require firstly comparison. And based on the comparison result, we can perform subtraction or nothing. So what is required? Conditional operation. Conditional operation is required, right? So multiplication is different. We can just generate partial product. There's no condition. We can just generate a partial product like 10001 or 0000, right? But in division, we firstly compare the value, and then based on the comparison result, and then we can just perform subtraction or nothing. So because division includes this comparison and conditional branch, right? Conditional branch operation. So division is more complex. And then actually it's very difficult to parallelize division, right? So because we have this comparison and conditional operation, okay? So if a certain operation includes conditional operation, then parallelization is very difficult, right? So this is the division. So actually, you can find that division is the inverse process of multiplication, but this inverse process includes the comparison and subtraction. So that's why the division is very difficult to parallelize. Okay, so but the overall, actually the naive algorithm, naive hardware is it looks similar to multiplier, naive multiplier, right? So we can just firstly check the first 4 digits and then compare the magnitude, and then we can generate the quotient. And then based on the result, we can perform subtraction or nothing. Okay. So this is some control large hardware. So you can find that looks a lot like a multiplier, right? Because it's the inverse process. Okay. But the division is, as I mentioned, the division is difficult for parallelizing. Okay, so but we can just implement also faster divider. Okay, faster division, like we can implement some fast division like the SRT division. Okay, but it also requires the multiple clocks or multiple steps. Okay. The RISC-V also supports the division instructions if we use M extension, right? So it's you can use the div or REM. So it means the div just generate the quotient, right? And then REM, so we can get the remainder. Okay, it's similar to the modular instruction, right? Modular instruction in C. So if we use A divided by B, then we can get quotient in C, right? If we just use the A, what is this? Modular B, then we can get the remainder in C, right? So, RISC-V also supports the this instruction, division and remainder. And then also, if we use the unsigned number, we can use the divu and the remainder u. Okay. So this is the multiplication and division operation in RISC-V or in CPU, right? And then we will learn about the floating point. So until this point, so we just handle integer instructions. So it means these instructions handle integer numbers, right? So you know the integer numbers are very simple, but we also frequently handle floating point numbers, right? So actually, it's those numbers, the floating point numbers are more common, right? So because so this is kind of a real number in our real world, right? So and then so you know so we already know that integers are very simple, but we can so we need to also use the floating point number. So which means the computer hardware needs to support floating point numbers. So this number system is getting more important because so you know the we are so the AI applications are very popular, and then actually the baseline AI applications use floating point numbers, right? But if you study these floating point numbers, then you can find that floating point numbers are more complex. So it's much more complex than integer numbers. So which means that the hardware that support floating point numbers will be also much more complex. Okay, so complex hardware, it's not good, right? Cost is high and performance is low, right? So in order to reduce the cost and then also in order to improve the performance, we can apply some different different number formats for AI applications, right? But the baseline number formats for AI application is floating point numbers, right? So it's important. So you need to understand how the floating point numbers are represented in a computer. Okay. Okay, so let's see the floating point number. The floating point numbers is the non-integer number, right? So it means in the real world, so we frequently use the numbers like 100.1234 like this. So this is the example of floating point numbers, right? So we can also represent the floating point numbers using the normalized form. So this is the example of normalized form. So what is the normalized form of decimal floating point numbers? It has sign bit, right? Obviously. And then it has one digit of decimal number and the point, and then it has the, the fraction part. And it is multiplied by 10 power of 10. Okay. So this is the normalized form of decimal floating point numbers, right? So we can also use the not normalized form like this example, but this is the kind of standard form, right? Standardized form It's normalized. Okay, so it's just some promise. So this is some default form. So it's a standard form of the decimal floating point number, right? Then in binary, we can also define normalized form of a floating point number. So this is the decimal number. So which means that each digit can have 10 different numbers from 0 to 9, right? Also, this base, the base is 10, okay? For the exponent part, the base is 10, and then we also use the decimal numbers for exponent. So this is the normalized form of a decimal floating point number. Then how about the binary number? So the same. We can apply the same approach, okay? Sign bit, and then one digit. So this is the normalized form. And then, but in binary number, we can have only 1 and 0. And then if we use the 0 here, then it's not normalized form, right? So what does that mean? We need to use only 1 here, right? Because, if we use the 0 in this position, in the floating point number, this is the not normalized form, okay? So this number is always 1 in floating point number. And then we can use any numbers for this part, okay? But we can use only 1 and 0, right? And then base is 2. And then for the exponent part, we can also use any numbers, any 1 and 0, right? Then what does that mean? So what is required for representing floating point numbers in binary number system? We need to represent sign bit, right? Obviously. And then this number is always 1. So we don't need to use any numbers, right? And then in order to represent this part, we require the binary numbers. And then base is always 2, so we don't need to use this number. And then we require this number, exponent part. So what are required? Sign bit. This part is called the fraction part. And then this is exponent part. So these are 3 kinds of numbers are required for representing floating point numbers, okay? And then in C, we can use the float data type and then double data type, okay? So what is the size of float and what is the size of double? In C, it's 4 byte and then it's 8 byte. What does it mean? Float, we can use the 32 bit because it's a 4 byte, and then double, we can use the 64 bit, okay, because this is the 8 byte. So it means actually this floating point representation is defined by IEEE standard. Okay, so this is the IEEE standard, and then actually we can use 2 representations, like single precision is a 32-bit representation of a floating point number. So it's float in C, okay, in C. And then double precision use 64-bit representation. So it's the double in C, okay? So there are 2 representations for these floating point numbers, okay? Okay, let's see how we can represent a floating point number. So as I mentioned, we require sign bit and then fraction part and exponent part. So we just allocate these numbers in the 32-bit format or 64-bit format. Okay, 32-bit a single precision format or 64-bit double precision format. Okay, so this is the equation. So we can, when we represent the floating point number x, then firstly we need to use the sign bit. So first bit is the sign bit, and the exponent part. The exponent part is the power of 2, so this number. So exponent part is represented like this. This is the exponent number. So this number is allocated to this field. So for the single precision floating point type, it has 8 bits, and then for the double, then it has 11 bits. Okay, and then fraction. So this is the 1.xxxs. So this part is the fraction part. So for the single precision, we use 23 bits for the fraction part. Okay, and then double precision, we use 52 bits. Okay, so this is definition, so, right? So it's just the definition. So you can just understand actually memorize the this definition. Okay, so you can find the bias. Okay, bias. So you may think that if we see the like a floating point number like a plus minus 1.xxxx multiplied by 2 to the power of exponent, okay, then we know these numbers are always positive number, right? Because x, this number is x, so this is sign bit. Okay, how about the exponent? We can use negative number, right? It's negative for the exponent part. Then you may think, oh, we can use the 2's complement number like integer for the exponent part. But in this floating point format, we do not use 2's complement number. Okay, so we just use the bias number. So actually, this number is the exponent minus bias. So what does that mean? So in the single precision, the bias is the 127, right? So this is just half of the 8 bits, the half of half minus 1 actually. And then for the double precision, the bias is 1023. So as you can see, so this is 8 bit. So you can find that this is the 2 to the power of 7 minus 1. And then this number is the 2 to the power of 10 minus 1, right? So instead of 2's complement number, then we just use the bias number to represent the minus number. So what does that mean? If this exponent number is 128, then what is the real exponent number? This part is the 128 minus 127. So it's 1. So do you understand? If we just use the 126 for this exponent field, then the real exponent is the 126 minus bias 127. It's minus 1, right? It's not 2's complement number. We can just use the bias to represent the minus number. Okay? It's a little bit different. So, and then exponent. So actually for the exponent, we cannot actually 0, 0, 0, 0, all zeros, and then all ones are reserved for special format. So for the normal number, we can just use the exponent from 0, 0, 0, 0, 1. Where is that? 0001 to 11110 for normal representation. So, this is definition, right? So it's just the rule, right? So what is the smallest number then? The smallest number, the exponent is 0.00001, right? Right, because the normal number, I mentioned that the 0.0.0 and 1.1.1.1 are just reserved. So we can just use for the normal representation, we can use only 0, 1 to 1.1.1.0. So actual exponent is, if we can just minus bias, then it's a minus 126. And then what's the smallest number? It's the 1 point xxx, the fraction part. So fraction part is always positive number. So O 0. So it's the smallest. So when you just consider magnitude of the number, so significant becomes the 1.0. So this is the smallest number, okay, of single precision floating point number. And then in a decimal number, it's similar, it's around the 1.2 multiplied by 10 power of 10 to the power of minus 38. The largest number, exponent part, is the 11110, right? So because all ones are reserved for special numbers, okay? The actual exponent is plus 127, and then so all fractions becomes 11111, okay? Then, so 1 point, many ones, 1111. So, this is the 1 over 2 plus 1 over 4 plus 1 over 8 plus blah, blah. And then this number is similar to 1, right? So if this number is very large, right? If it goes to the infinite, then it's similar to the 1, right? Right? It's a mathematics, right? So it's similar. It's not 2 exactly. It's not 2 exactly, but it's around 2. It's similar to 2, right? 1.11111. What is it? 1 over 2, 1 over 4 plus blah, 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 blah. So this is the largest value. So it's similar to 3.4 multiplied by 10 power of 38. Double precision is the same, but the exponent part has more bits, right? So you can just apply the same approach. Then this is the smallest value, and then this is the largest value. So this is the largest, smallest decimal floating point number, and this is the largest decimal floating point number. They can be represented by double precision floating point numbers, right? So precision. So let's see the precision of the floating point number. Okay. So the precision is determined by fraction part, right? And then this fraction part is x multiplied 1 over 2 and plus x multiplied 1 over 4, blah, 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 right? So this fraction part decides the precision, the precision of the floating point number. So if the single precision, we use the 23-bit for the fraction part. So right, so it's approximately 2 to the power of 23, right? So if it's similar to so when we just represent this precision for using for the decimal number, then it's similar to the 6th decimal number, okay? And then for the double precision, this is approximately 2 to the power of minus 52, obviously. And then it is equivalent nearly equivalent to the 16 decimal digit of precision. And then single is a 6 decimal. So what does that mean? It is equivalent to the 2.12345 this amount of precision. Okay, the 6 decimal numbers. Okay, so this is the limitation because so actually we already know that in the real number, in the decimal number, actually we cannot represent the exact numbers using decimal format, right? So if we, because it's just like infinite, right? If we just use the 1.2345 and then infinite digit, but infinite digit is not possible, right? So it means actually it has also our decimal numbers has the limited precision. It's the same. It's the same for the binary numbers, right? But you can understand that for the single precision, it is similar to the 6 decimal number precision. And then if we use the double precision floating point numbers, the precision of this double floating point number, then it's equivalent to 16 decimal digit of precision. Okay, it's just limitation. Okay. Okay, so this is the example. So how can we represent the floating point number? So this is minus 0.75. So minus 0.75. So this is the minus number, obviously, right? It's the minus number. And then what is the 75? It's the 1 over 2 plus 1 over 4, right? It's actually 0.11 in binary number, right? So we can represent, so in the normalized form, we can represent this number as like this. So sine bit is 1. This is the fraction. This is the exponent. Sine bit is 1. And then the fraction is 1. So it's the 1, 0, 0, 0, right? And then what is this number? This number should be exponent minus bias is minus 1. And then what is this bias number? 127, right? So real exponent is the 1 minus 1 plus bias, right? Here. So it's 126 for the single precision number, single precision floating point number. And then for the double, the bias is 1023. So it's 1022. So we can convert the decimal floating point number to the single precision or double precision floating point number like this. It's just a rule. It's just a definition, right? So we can just convert based on the definition, right? So this is the inverse process. So we can just also represent, we can just convert the floating point number to the decimal floating point number. Okay. So this is the example. So then if we just analyze this number, then sine bit is 1, and then this is the exponent part. The exponent part is 10001, and then this is the fraction part. And then based on the definition, we can just use this number. So right, this is the sine bit, and then exponent is 129, but it's 120. Actually, the real exponent is 129 minus bias, it's 2, right? So here, and then the fraction part is 0, 1, 0, 0, 0. So it's a 1.01. Okay, so 0.1. So it's if this means the 1 over 4, right? It's 0.25, right? 0.25, so sorry. So it's a 1.25 multiplied by 2 to the power of 2. So it's minus 5. So conversion. So conversion, we can just convert the floating point to decimal or decimal to floating point based on the definition. So IEEE floating point definition, right? Okay, so let's see the denormal number. So I mentioned that if exponent 0, 0, 0, 0, and then exponent 1, 1, 1, all ones are reserved. For normal representation, we can just use the 1 to the 1, 1, 1, 1, 0, right? For the exponent number. Then, why? So, then exponent 0, 0, 0, all zeros are used for representing denormal numbers. Right? It's a denormal. It's not a normal. Okay? So, denormal number. So, if the exponent is 0, 0, 0, then it means it's very small. The size is very small. Then we can just represent this number like this. So sign B is the same, but if the exponent is 0, all zeros, then instead of 1, it just use the 1 plus fraction. Okay, so this is different. And so we use the 2 to the minus bias plus 1. Okay, so for the single precision, it's 127 plus 1. It's a minus 126. Okay, so denormal number. So actually, the all zeros, if the exponent number is all zeros, which means that it's very small number. So we just slightly change the some this representation. So it is used for represent a very small number. So smaller, this number is smaller than normal numbers, right? And then it allows for gradual underflow and then some very small. It is used for representing very small numbers, small values. And then how about the 0 then? 0 is the smallest value. So if we just consider the magnitude, right? 0 is the smallest value. So if all exponent is 0 and then all fractions is 0, then it is the 0, right? Sign B can be 1 or 0, right? So fraction part is 0. So because the exponent is 0, then we need to use this format, right? So it starts with 0. So 0 plus 0. And then all fraction part is 0. So it's a 0 plus 0 and then multiply by this 1. So it's minus 0. It can be plus 0 or minus 0 based on the sign B. But actually, these numbers are 0. So actually, for the floating point numbers, we have two representations for 0, the 0.0. Then if you see this one, then you can understand why. Why do we use this normal number format, right? Why? If we just use the normal number format like x minus 1, s plus multiply by x 1 plus fraction, and then multiply to the power of exponent minus bias, and then if this is a 0 and then this is a 0, then what's the real number? It's the 1.0 multiply very small number and then plus minus. It's not 0, right? Do you understand? So if we just apply the normal definition, so for the normal representation, then problem is that this number is 1. So we cannot represent 0, right? So that's why we just apply the special format, for exponent number, all zeros. Okay, all zeros exponent number. Okay, so then we can represent the 0. Do you understand? Okay, so just remember, so it's a definition, right? So it's a definition. So just you can just remember that if the all exponent part is R0, then it can be, it represent this format. Okay, and then what if the all exponents bits are ones, then it represent the infinity or not a number. What does it mean? So this is the special format. Okay, so all exponent parts are ones, and then fraction is 0, 0, 0. Then it just represent the infinity, right? So it cannot be represented using normal floating point format. So which means we can just identify the very large number. It's not real infinite, but if this large number cannot be represented using the floating point formats, then we need to identify this. So in order to represent this large number, then we need to use the exponent 1, 1, 1, 1, 1, and then all fraction parts are 0. So it means it's the infinity number, plus minus infinity. Okay, it's not real infinity, right? But anyway, it's a very large number. So, and then if we just use the all exponent part ones, okay, and then, but if the fraction part is not 0, okay, then it represents not a number. It's not a number. It's called a NaN, okay? So you can sometimes observe the not a number in Excel, right? So if we cannot represent it by using the numbers, then so it's a kind of some it's a errors, but sometimes we cannot represent some numbers, some equations. For example, divide by 0. We cannot represent divide by 0. So in this case, we can use the not a number. Okay. So if the all exponents are ones, then we can represent. It is used for representing infinity, very large number, and then not a number. Okay. So some. Okay. Then let's see how can we apply some arithmetic operations for floating point number. It's the same, right? For the decimal number. So think about the decimal number. How can you calculate this? We cannot directly calculate this addition. Why? Because the exponents are different. So what is required? We need to align decimal point, and then if the decimal point is the same, then we can calculate the addition for this number, the significant, and then we can get the result. But it's not normalized, right? So then we can normalize the result. Then can also round the result if necessary. So this is the floating point addition in decimal number. Binary, the same, right? So this is the example. And then also we need to align binary point, right? Because if these exponents are different, we cannot directly calculate. The firstly, align binary points, and then apply addition for the significant, right? And then normalize the result. It's the same. So what does that mean? Our hardware, the floating point adder, also needs to perform these steps, right? So, and then you can find that these steps are more complex than integer arithmetic. So integer arithmetic, we can just perform addition directly for integer numbers, right? But for floating point arithmetic, then we need to perform multiple steps like this. But you know, it's same. It's the same for the decimal numbers, right? So these steps are required. So this is the addition, but it's more complex. That's why the floating point ALUs or floating point processing engines are more complex than integer engines. Okay. So this is the floating point adder hardware, but it just performs the required steps. Okay, like the aligning and then some the addition for the significant and then normalize and then round. Okay, so you can find that it's more complex. So it's pipelined also. Okay, it can be pipelined. How about the multiplication? So multiplication, so we can just add exponent. So actually we don't need to align this exponent part, right? And then multiply significant and then normalize the result and then round we can just perform round if necessary, right? But you can find that this part is a little bit different, right? So because we can just perform the addition for the exponent, okay? But this step is similar to floating point add. And then the final step is we can just check the sign bit, right? It's because plus multiply plus is a plus, plus multiply minus is a minus. But it's very simple, right? So floating point binary, the same, right? Add exponent, multiply significant, normalize, round, and determining sign bit, right? So floating point arithmetic also, it's more complex. Obviously, it's more complex than integer arithmetic. And then also we need to perform multiple steps like this. Okay, so we need also we need to implement the hardware that performs these multiple steps. Okay, and then also it can be pipelined. Okay, and then the complexity is similar. So, you know, the floating point adder is also complex. Floating point multiplication is also complex. Okay. So it takes several cycles. So the RISC-V, actually, in order to support the floating point numbers, RISC-V has separate registers, separate floating point registers. It's called from F0 to F31. Okay, so if our CPU supports the integer and floating point numbers, our CPU includes the integer registers, right? Like X0 to X31 for RISC-V. And then also it includes the registers for floating point numbers from F0 to F31. Okay. So, and then also RISC-V includes the instructions that handle floating point numbers. Like, so for example, load instruction, if we just perform memory instruction, then the destination of this memory, like the load instruction needs to be floating point registers. So we need to use the FLW or FLD. Okay. Also, the store instruction is the same. So if we just add the F in front of the instruction, then it means the floating point instruction. Other instruction is the same, like F add and F mul or F divide. But you can find the postfix here because it's .s. This postfix represents the single precision. It's a single precision of precision. Okay. And then if we just add .d, then it represents the double precision. Okay. So this is the floating point instructions. Again, also we can perform the comparison instructions. Okay. And also we can also implement the branch instructions based on the floating point condition. Okay. So this is the example of a floating point instructions in RISC-V, right? But don't worry about that. So we actually in this course, we will just cover only integer instructions, right? But this is just example, the example code in the assembly code for floating point numbers, okay? So, okay. So, okay. So I will stop here. So actually I covered the chapter 3, most part of the chapter 3. Okay. Okay. Any question? Okay. See you in the next class. 감사합니다.